3 red points appeared in James Webb's infrared view, scattered among galaxies so distant that their light had traveled for more than 13 billion years. Then the picture changed. Something was wrong. The 3 points were not 3 objects. They were 3 distorted images of the same tiny source, copied by gravity like one face reflected through broken glass. But the real impossibility was not that one object appeared in 3 places. It was what Webb found inside it, and what should have surrounded it but did not. The scientific risk was enormous. If the measurement survived, the familiar birth order of galaxies could be wrong. Gas rushed around an invisible center. One side moved toward us, the other pulled away. The closer it came to that darkness, the faster it moved, as if the gas were circling an enormous weight, hidden inside a world that had barely begun to exist. That motion allowed astronomers to weigh the unseen object. The answer was astonishing. About 50 million suns. Now hold that number. The system, called Abel 2744 QSO1, existed when the universe was only about 700 million years old, yet Webb could find room for fewer than 20 million suns in all the stars around the center. The black hole was not a small heart inside a vast galaxy. It outweighed the entire stellar body that was supposed to have created and fed it. You do not need to understand a single equation to feel the contradiction. The child appears older than its parent. The shadow arrives before the object expected to cast it. And if Webb is right, the loss is not one minor detail in a textbook. It is the starting point of the entire story. In the nearby universe, a giant galaxy normally surrounds its central black hole like a city around one dark building. QSO1 looked like the opposite. The foundation was already heavier than every building above it, and most of the city had not even been constructed. That is what shouldn't be possible means here. No law of physics was broken. The familiar order was. Stars were supposed to come first, some were supposed to die into small black holes, and those remnants were supposed to grow slowly inside a galaxy. Webb found the apparent result before it could find enough of the expected cause. And the deeper astronomers looked, the more of that cause seemed to disappear. First, the galaxy was missing. Then the chemical fingerprints of earlier stars were missing. Finally, the 2 most dramatic explanations both ran into trouble. By the end of this story, those 3 harmless red points will no longer look like a visual trick. They may be evidence that in at least one corner of the infant universe, darkness came first, and the galaxy was forced to catch up. For modern astronomy, galaxies and supermassive black holes have looked inseparable. Most large nearby galaxies hold a giant black hole at the center. Our own Milky Way holds Sagittarius A star, a black hole about 4 million times the mass of the Sun. Far larger galaxies contain black holes weighing billions of suns. That relationship feels almost natural because galaxies provide gas, stars, dust, and smaller black holes. Over time, the central object feeds, merges, and grows, while energy released near it heats or drives away gas and changes how quickly new stars form. The galaxy shapes the black hole shapes the galaxy. They grow together. But every family story has a beginning, and this one has always contained a hidden problem. There was one problem. The first real pressure was time, because the young universe had not existed long enough to waste any of it. The first stars were born from hydrogen and helium left after the Big Bang. The most massive of them lived quickly and died violently, leaving black holes tens or hundreds of times heavier than the Sun. Those remnants could then consume gas and collide with other black holes until, given enough time, small seeds became monsters. The early universe did not offer enough time. Nothing in the familiar story removed that pressure. Astronomers have found quasars powered by black holes millions or billions of times the Sun's mass within the universe's first billion years. Building one from an ordinary stellar remnant demands an extraordinary feeding pace maintained for long periods without starvation or ejection during mergers. Favorable conditions can do it, but the timeline is brutally tight. Think of trying to grow a sapling into a forest before sunrise. Every minute matters, and if you lose one long stretch of growth, the entire schedule collapses. Your seed has no second chance to recover the lost time. QSO1 makes that schedule even harder because its light began traveling toward us more than 13 billion years ago. At that age, the universe had reached only about 5% of its current lifetime. The system itself spans about 1,100 light years. That sounds enormous until you compare it with the Milky Way's width of about 100,000 light years. QSO1 is a compact ember beside a sprawling modern city, and your entire mental picture of scale begins to turn inside out. Yet that ember hides 50 million suns in one central point. At first, there was an easy way to soften the mystery. Perhaps the early numbers were simply wrong. Webb had discovered many compact objects now called little red dots. Some seemed to contain feeding black holes, but their masses were usually estimated from the brightness and speed of glowing gas using rules tested on galaxies much closer to home. Nobody knew whether those rules still worked more than 13 billion years in the past. If the strange gas around little red dots fooled the calculation, their black holes might be 10 or even 100 times lighter than claimed. You can feel the relief in that possibility. Shrink the monsters, and the young universe regains enough time to build them in the familiar way. But QS01 offered a rare chance to test that escape. Here is where the first comfortable answer began to fail, and the pressure moved from theory into a direct measurement. The object sits behind Abel 2744, nicknamed Pandora's cluster. The cluster's gravity bends the path of QS01's ancient light. This effect, called gravitational lensing, magnifies the distant source and produces 3 separate images of the same red dot. The cluster did not create extra black holes. It created extra paths for the same light. Picture a patterned tile seen through a warped piece of glass. From where you stand, the tile can stretch, brighten, or appear more than once, but every distorted image still traces the same original object. On a cosmic scale, Pandora's cluster became that warped glass. It handed Webb a natural magnifying lens far larger than anything humanity could build. Without it, QS01 would have remained too compressed for this experiment. With it, the tiny red point was stretched enough for Webb to trace motion within the gas itself. The universe had placed a magnifying glass in exactly the right line of sight, but that created a harder challenge. Webb still had to turn stretched light into a trustworthy weight. And Webb used more than a camera. It split the ancient light apart and followed hydrogen moving across the source, turning a red speck into a tiny map of motion. One side of the gas came toward Earth, the other moved away. That was enough to expose the hidden weight. If millions of ordinary stars were spread across the center, their gravity would also be spread out. The gas would respond to a broad crowd of objects. Instead, it sped up sharply as it approached one tiny region, following the same simple pattern that makes Mercury move faster around the Sun than distant Neptune. The orbit became a scale. For the first time within the universe's first billion years, astronomers were no longer estimating this black hole only from how brightly the surrounding gas shone. They were watching matter move around it and using that motion to measure the mass directly. The result landed near 50 million suns. The team tested whether a dense star cluster or an unusual pile of dark matter could imitate the motion. Each alternative failed unless its mass was squeezed into an almost impossibly small point. In other words, unless it behaved like the black hole it was meant to replace. The easy escape collapsed. The earlier estimate had not exaggerated a modest black hole into a monster. Astonishingly, the monster survived the test. Now the harder question moved outward. If the center contained 50 million suns, where was the galaxy that had built and fed it? The rotation curve left little room for one. It placed a conservative upper limit of about 20 million solar masses on all the surrounding stars, making the black hole to stellar mass ratio greater than 2. The dark center outweighs every star the host could contain. Compare that with the relationship around us. In nearby galaxies, a supermassive black hole usually represents only a small fraction of its host's stellar mass, while QS01 sits orders of magnitude above that familiar pattern, and about 10 times farther above it than even some of the most extreme early systems Webb had previously uncovered. This is why the phrase naked black hole appears in discussions of the discovery. It does not mean the object lacks gas or emits no light, since the black hole is actively accreting and the surrounding hydrogen glows. It means the massive stellar body expected around such an object is astonishingly weak or absent. The city is missing, and without it the old origin story faces an irreversible failure. And then Webb found a second form of emptiness. This is the moment the discovery becomes more than a large number. You are no longer looking for a hidden object. You are looking for a missing past, the generations of stars that should have lived, died, and left evidence behind before a black hole could grow this large. Stars do more than shine, they manufacture heavier elements. The Big Bang produced mostly hydrogen and helium with traces of a few lighter nuclei, while carbon, oxygen, silicon, iron, and much of the material associated with planets and life were forged later inside stars or in violent stellar deaths. So a gas cloud rich in oxygen carries a history, telling you that earlier stars lived, processed primitive material, and returned the products to space. A chemically pristine cloud tells the opposite story because it has not been heavily recycled through generations of stars. The gas across QS01 is almost entirely hydrogen and helium, and its metallicity, the astronomers' shorthand for elements heavier than helium, is below 0.5% of the Sun's, making this one of the most chemically pristine galactic environments ever measured. Keep that number beside the missing starlight and let it change what you think you're looking at. Less than half of 1% of the Sun's heavy element abundance surrounding a black hole with the mass of 50 million suns. The system is not merely short of stars now. Its chemistry records no rich chain of previous stellar generations capable of building such a black hole by the ordinary route. That was the breaking clue. The simple story says stars came first, massive stars collapsed, and their black holes fed and merged. But QSO1 presents a central object larger than its allowed stellar host inside gas, carrying almost no record of the stellar history required to make it. The expected cause is absent, while the supposed result is already enormous. For a moment, set aside every exotic label and follow only the evidence in the order Webb delivered it. Hydrogen motion points to a compact central mass of about 50 million suns. The stellar host stays below 20 million. The environment is nearly pristine, and the system stands just 700 million years after the Big Bang. Those are the measured pieces. The conclusion is not that Webb photographed the instant this black hole was born. It did not, and the light shows QSO1 at one early stage rather than its complete childhood. But ordinary stellar growth has so little material, chemical history, and time to work with that. The black hole was almost certainly born as a heavy seed, already far larger than the remnants of normal stars. And this is where the mystery splits into two extraordinary paths. The first possibility begins not with a star, but with an enormous cloud of primordial gas, which under the right conditions collapses inward so rapidly that it avoids fragmenting into many ordinary stars. Instead, the central region falls almost directly into a black hole, creating a seed thousands or tens of thousands of times the sun's mass. Such a direct collapse black hole would begin the race far ahead of a stellar remnant, still feeding and merging, but avoiding the desperate climb from 10 suns to millions, one small step at a time. The image is unsettlingly simple. No long stellar life, no supernova, no familiar death, as a cloud larger than any object in the human world folds inward and its center vanishes behind a horizon before a normal galaxy can fully ignite. Direct collapse has been theorized for years, and QSO1 looks like the kind of system that should favor it. Young, compact, gas-rich, and chemically primitive. But there is a problem. Many direct collapse scenarios need a strong nearby source of ultraviolet radiation, which destroys molecular hydrogen and prevents the gas from cooling and breaking into ordinary stars before the full cloud collapses. In the neighborhood of QSO1, no powerful ultraviolet source stands where many versions of this pathway expect one, not even the remnant of a nearby starburst that supplied it earlier. The mass ratio creates another strain. Even models that begin with a heavy seed struggle to place more mass in the black hole than in the young stellar system around it. QSO1 does exactly that. Direct collapse remains possible through variants operating in different environments. Yet the most obvious version does not slide neatly over the evidence. The first answer works, then it catches. The second possibility reaches much farther back, into the universe's first second, when tiny density variations in the hot, newborn cosmos could collapse directly into primordial black holes before stars, galaxies, or even atoms existed. Their proposed masses span a wide theoretical range, and no primordial origin has been confirmed for a system like QSO1. If QSO1 descended from such an object, the order of creation changes completely, because the black hole would not be the corpse of a star or the final product of a galaxy. It would be an ancient gravitational seed waiting for ordinary matter to cool around it. That possibility fits one clue beautifully. A primordial black hole needs no stellar ancestry, so the pristine hydrogen and helium around QSO1 stop being a contradiction, and the darkness genuinely comes first. But this path catches too. The observed black hole weighs about 50 million suns, while one primordial scenario discussed by the researchers naturally favors seeds closer to 1 million. QSO1 is far heavier, so even a black hole born before the first stars would still need intense feeding or rapid mergers to reach the mass Webb measured. So neither door leads to an effortless answer. Direct collapse needs conditions that are not clearly present, while a primordial origin reaches back to unconfirmed physics and still requires major growth. The observation points strongly toward a heavy seed, but it does not tell us which kind. This uncertainty is not a weakness in the story. It is the reason the discovery matters, and it places you beside astronomers at the edge of what the evidence can currently decide. You can choose the giant collapsing cloud or the black hole born before starlight. Neither choice removes the pressure. Each saves one part of the evidence and loses a clean explanation somewhere else. Science rarely changes, because one object arrives carrying a perfect label. It changes when an object removes comfortable explanations faster than new ones can replace them. QSO1 has done exactly that. The ordinary small seed route struggles. The inflated mass escape has been directly tested and weakened. A large hidden stellar host is restricted by dynamics and light, and a rich history of previous stars is contradicted by the chemistry. What remains is narrower, stranger, and far more consequential, and now comes the part that turns one extreme black hole into a problem for the entire early universe. Now return to those 3 red images, which were produced by one source, but also reveal something essential about the method behind this discovery. Webb did not simply take a photograph of a black hole. Black holes emit no light of their own, and the colored frame is a processed infrared view rather than what your unaided eyes would see. The telescope assembled an indirect portrait from motion, chemistry, and gravity. Pandora's cluster magnified the red dot. Hydrogen traced the orbit. The orbit revealed the concentrated mass. Missing starlight limited the host, and the primitive gas exposed the missing stellar past. One clue would have been provocative. Together, they form a chain, and the chain leads beyond QSO1. Webb has discovered many little red dots in the early universe, compact, unusual sources whose light often carries signs of feeding black holes. Their unexpected abundance became one of Webb's most extraordinary surprises. If QSO1 were a solitary cosmic accident, astronomers could treat it as an extreme corner case, but little red dots make up an estimated 15 to 30% of the known actively feeding black holes of this kind in that distant era. That raises the stakes from one anomaly to a hidden population. That does not mean every little red dot contains a naked 50 million solar mass seed. Their nature is still being investigated, and QSO1 benefited from exceptional gravitational magnification. But it opens the real possibility that many systems began black hole growth earlier, faster or from heavier seeds than the classical story allowed. The team is now analyzing similar objects, and each one offers a test that you can state without technical language. If their gas also rotates around overmassive central points, if their stellar hosts remain faint, and if their chemistry stays primitive, QSO1 will stop looking like an exception. It will begin looking like a phase, an entire chapter of cosmic history that we failed to see before Webb. That shift would change how we picture the first galaxies. The familiar version begins with dark matter halos collecting gas, the gas cooling, stars igniting, some dying into black holes, and those remnants moving toward the center until they merge, feed, and influence the mature galaxy around them. But a heavy seed reverses the emphasis, placing a black hole early inside a young halo where it captures gas, releases enormous energy as matter falls inward, and regulates the environment from the beginning. The galaxy and black hole still grow together, but they do not start as equals. The black hole begins with an impossible-looking head start. But that answer created a new problem. If you move the black hole to the beginning, you must explain how nature made it. You can think of gravity here as scaffolding, but do not picture the black hole building stars by magic or single-handedly creating its galaxy. What matters is that a 50 million solar mass center changes where gas collects, how quickly it moves, and how much energy it releases while falling inward. The seed is not waiting passively at the end of galactic evolution, because it is present during construction. That helps explain a much older puzzle, why so many enormous black holes already existed when the universe was young, because some of them did not win an impossible growth race. They started closer to the finish line. To feel the scale of that advantage, give two seeds the same cosmic clock, and let one begin at 10 solar masses, while the other begins at 10,000 or 1 million. Even if both feed efficiently, the heavier seed skips generations of doubling, avoids years when a small remnant would be vulnerable to starvation or ejection, and reaches the realm of quasars, while its smaller rival is still struggling through the earliest climb. You do not need the exact growth equation to see the consequence. Changing the starting mass changes which black holes can exist before the first billion-year mark. And that answer created another pressure point. A heavy seed cannot remain merely a convenient mathematical starting value. Nature has to make it somewhere, under conditions that leave recognizable traces in surrounding gas, nearby galaxies, merger histories, and the distribution of later black hole masses. QSO1 gives researchers a place to search for those traces, but it also makes every missing trace more important. There is another quiet detail in QSO1 that makes this moment even stranger. The black hole is feeding at only about 1 or 2% of the rate associated with its theoretical brightness limit. Webb is not catching it during its greatest feast. The black hole must have gained most of its mass earlier through faster feeding, mergers or both, before entering the calmer phase recorded in the light we now observe. The monster is enormous, and astonishingly it is resting. Its present calm cannot reveal every earlier burst of growth, and mergers would bury much of their history inside the final mass. Webb sees the result, not every step that produced it. Future observations must turn that hidden history into a testable one by mapping more little red dots, searching for stellar hosts at greater sensitivity, comparing chemical abundances, and measuring whether gas follows the same central rotation. A population matters more than one spectacular object, because each origin pathway predicts different environments, masses, neighbors, and growth patterns. Gravitational waves offer another route, because mergers between massive seeds in the young universe shake spacetime at frequencies future observatories are designed to pursue. Those signals can reveal whether early black holes assembled through repeated collisions and whether their starting masses were already enormous. Until then, QSO1 remains extraordinary evidence rather than a final verdict, and you're left with one honest frontier instead of a manufactured answer. Here's what the data actually show. A directly measured supermassive black hole of about 50 million solar masses in a system seen only 700 million years after the Big Bang. The team interprets its extreme mass ratio and nearly pristine surroundings as evidence that it formed from a heavy seed before a substantial stellar galaxy developed. The more provocative possibilities are direct collapse from a giant gas cloud or descent from a primordial black hole. Neither has been confirmed. That is the precise answer hidden inside the title. Webb did not witness a black hole forming before its galaxy, and it did not find an object forbidden by physics. It found a black hole so massive, so early, so dominant, and so chemically disconnected from ordinary stellar ancestry that the conventional star's first route cannot comfortably explain it. The black hole arrived first in the evidence we can reconstruct, and the galaxy is still catching up. Return once more to the opening frame, 3 small red points scattered through Pandora's cluster, and notice how your understanding has changed. Before this investigation, they looked like a visual trick created by gravity, but now they carry the weight of a different cosmic order. The light in those points began its journey before Earth existed, before the Sun existed, and before the Milky Way had taken its present shape. For more than 13 billion years, it crossed expanding space, entered Webb's mirror, passed through a spectrograph, and broke into a pattern of approaching and receding hydrogen. From that faint motion, we weighed the darkness, and the weight was greater than the world around it. For decades, humanity has treated supermassive black holes as the dark hearts of galaxies, objects that grow inside vast stellar systems and later help shape them. QS01 asks you to hold a more unsettling image, a dark heart beating before most of the body exists, and drawing the first structures around itself in a universe still almost chemically untouched. If future observations find that this pattern repeats, the change will reach far beyond one little red dot, and textbook diagrams will need a second beginning. Some galaxies made their black holes, while some black holes helped make their galaxies. And perhaps the first great structures in the universe did not begin with light. They began with gravity, gathering silently around something we still cannot fully explain. If you want to follow the next evidence Webb uncovers from the universe's hidden beginning, subscribe to Cosmos Cipher, because somewhere inside another tiny red point, the answer is already traveling toward us, and one day it may change the cosmic story you thought you knew.